Okay, so the last talk of today will be given by Jérémie Bigot from Université de Bordeaux.
Okay, so thanks a lot to the organizers of this workshop and for the invitation opportunity to present this work here. So this is a joint work with a colleague from my university in Bordeaux, Bernard Bercu. And the idea of this work, it's a recent work, it was to discuss some statistical aspects of a method called stochastic algorithm for optimal transport, which has been recently introduced by Aude Genevet in her PhD work that has been supervised by Gabriel, and I don't think there are other people in the room, no, who have proposed this work. So actually I have to say that it's a recent work and I have more questions than probably results to present, and I hope that some people will be interested by the questions that I have. The questions are, is it useful to do data analysis, this kind of approach? And also we will see that there is something that is called entropic regularization. So there is, behind this method, there is a regularization parameter, and I would like to discuss the choice of this parameter taking the point of view of a statistician. Okay, so first I will present some data which motivates the use of this algorithm, and it's a problem of resource allocation. So I have taken data from the website of the city of Chicago. So you have you have open data on many different things happening in Chicago. And the data that I am considering are the following. You have the location of police station in Chicago. And over 1 year, you have the spatial locations of reported incidents of crimes, with the exception of murders, but you can also have murders on this website. So some questions maybe of interest are, given the location of a crime, which police station should intervene, and how you update the answer in some online fashion when you have new events coming. So very often when you have presentation on resource allocation problems, you have a problem of pizza delivery. You have a call center, you have places where they produce pizza, and you have people somewhere in the city who are calling to have a pizza, and the problem is which pizza station, I don't know, should deliver the order. So here it's taken from this website of Chicago. So the blue points are the location of the police stations. You have like 23 police stations, I think. So I denote this location by YIYJ. And then so sorry, I've not keep things with the Google Map things. Huh? So the blue points are again the location of the police station, and the red triangle is the first locations of a reported incident of crime in the year 2014. Okay? Then you have a second one, then a third one, and so on. And the question is, when you have a crime here, which police station should send someone to see what happens here. Okay, so along the year you have more and more data. Okay, I stop here. Okay, so it's the whole data, and of course here you don't see anything. So what you do heat map if you are not a statistician, and if you are a statistician, you do kernel density estimation. And what you see here, you see that, I don't know the city of Chicago, but it seems that in some part of the city you have much more crimes happening. Okay. Okay. So now, what is the link between this question and what is called Wasserstein optimal transport? Okay. So how do you model this problem? This is the way I choose to model the problem. So the spatial locations of reported incidents of crime, you consider them as a sequence of IID random variables that are sampled from some probability measure, mu, that has some support, but you don't know this probability measure. And on the other hand, you suppose that the locations of polystations, they are considered as being a known and discrete probability measure whose support or the location of the polystation. And here, because I had no other information, I took uniform weights, which means that the capacity of each polystation is the same. Okay, let's thinking this way. Okay, so now how to solve this resource allocation problem? So you assume that you want to find a map which transports the support of your unknown measure x to the location of the polystation in some optimal way. So in probability, you would say that the map T is transporting the absolutely continuous measure mu onto the discrete measure nu. And you want this map to be optimal in the sense that will be given just after. And it has to be optimal with respect to the choice of a cost function, which can be, for instance, a distance on the support x. And for example, we present result with the L2 or the L1 distance. Okay? And of course, you don't know this measure mu, so you only have samples from this measure, and it's a statistical problem of how you can estimate, once you have defined it, this map based on a sequence of IID data. Okay. So how do you define this map? So I guess that maybe not all of you are familiar with optimal transports. So I will just present some formulation of this problem. So you have your transport map here, which pushes forward nu onto nu. And you have two different formulations. The original one of optimal transport is called the Monge formulation. What you want to solve is this optimization problem. You move x to the location T of x, it costs something, and you average the cost of moving x to the location T of x with respect to the measure mu under this constraint of sending mu onto nu. Okay? And you have a relaxed version, which is called the Kantorovich formulation, and it's not formulated in terms of optimal maps. It is formulated in terms of what we call a transport plan. A transport plan is just a probability measure on the x times x with marginals mu and nu, and you also want to solve an optimization problem. Okay? And if you have metric properties for C, then this gives you a distance, for example, on the set of probability measure. Okay. So if we come back to our problem, this is called a problem of a semi-discrete optimal transport. Here you have mu, the colors, and it's a mixture of Gaussians in 2D. Okay, so you have an absolute continuous measure mu, and you have a discrete measure which is here whose locations are represented by the black points. Okay, and finding an optimal map is to have something like this. Here, what I represent is for the Euclidean cost. It's the results of the Monge formulation of optimal transports. Okay? What it shows you here, it gives you a partition of the support of the measure mu, and it says that all the points that are within a cell of the same color here, they are sent to this data point here. And the colors are proportional in some sense to the intensity of the measure mu. Okay. So another way to see this optimal mapping is to remark that it is a mapping from a continuous set in some sense to a discrete set. And actually, I will explain what it means later on. You can formulate a dual version of the Kantorovich formulation of optimal transports. and you end up with a maximization problem over a finite dimensional space, which is of the same dimension than the number of masses of the measure nu. And once you have found a maximizer of this dual version of Kantorovich formulations, then you can estimate the inverse of this by solving this problem, which in some sense represents, which is like a K-means problem, or the problem of computing Voronoi cells. And more generally, it's called, such sets are called Laguerre cells, and it's an important concept from computational geometry. And if you are interested by this, there are lots of papers by Quentin-Mérigot, and also the book by Couturier and Perret, where you can find lots of references on this concept. Okay, so now let us come back to the heart of this talk, which is regularized optimal transport and stochastic optimization. Okay, so it's solving a problem of optimal transport is a difficult linear program in its computational cost. Why? Because if you have two discrete measures with the same size of support, k, then the cost is cubic in the number of data points. Okay, and recently, and I think it has clearly been the starting point of the success of computational optimal transport for data analysis. So in 2013, Couturier has proposed to smooth the Kantorovich formulation of optimal transport by adding a strongly convex term to this linear program. And here, the term that you add, the regularization term that you add, it's the Kullback-Leibler divergence between P and the plan, which is simply the product between mu and nu. Okay? And here, okay, up to some constant, it's like the Kullback-Leibler divergence between two transport plans. Okay? And you have a very efficient algorithm to solve this problem. It's called the Sinkhorn algorithm. And its advantage is that you reduce the computational cost from a quadratic one, no, from a cubic one to a quadratic one at each iteration. Okay, okay, but still, you can think of other way of solving this problem. And this is the starting point of stochastic optimal transport, which has been proposed in this paper. And the point of view is to remark. So now I will only talk about the case where you have regularization. So here I always assume that the parameter epsilon is strictly positive. So now you can formulate a dual version of these problems, and you end up with, so now the problem is to calculate what is called a regularized Wasserstein distance. And actually you can remark, it's explained in this paper, that you can solve the maximization problem, but this time now over a finite dimensional set of a function which can be written as the expectation of some function which is very simple to compute. And the expectation is taken with respect to a random variable x, which is distributed according to the measure mu. Okay? And once you end up with an optimization problem of this term, because you have of this type, because you have now an expectation here, you can use the framework of stochastic optimization to obtain a solution, an approximate solution of this by sampling data from the distribution mu. Okay? And this is called well-known as Robbins-Monro algorithm, and this is okay, they are in this paper they are considering more refined version than just Robbins-Monro. But basically the idea is the following one: you want to find a minimizer of sorry, it's a maximizer. There is a max. You want to maximize this problem. You have a sequence of random variables which are and distributed according to mu. You just take a classical condition on the step size, And here it's just like a standard gradient descent, but here the gradient term, it is stochastic, and it evolves at each iteration the arrival of a new variable. Okay. So what is very nice here is that when you have regularization, it's very easy to compute the gradient. It's not important to have in mind the formula here. The only interesting thing is that P here, it's a probability measures of, it's a vector of dimension J with all coordinates positive, and that sum up to 1. Okay, so all of this to present what has been done before, and now I would like to give you a few results around our recent contribution. Okay, so actually, if you are familiar with stochastic optimization, so there is nothing really new. In the sense that this is a standard stochastic optimization problem with a smooth objective functions. So you have like hundreds, thousands of results on this. And what we have done first was just to apply standard results on stochastic optimization. And you can easily prove that you have a convergence of your sequence of your Robbins-Monro algorithm to a maximizer. You can also have asymptotic normality. And when you have to choose your step size, and it's very classical. Either you choose it as gamma over n or as gamma over n over c, and there are two different behaviors depending on the power that you have taken here. If you take a step which decays like 1 over n, then what is appearing is a condition on gamma which involves the smallest eigenvalues of your Hessian matrix. And when c is smaller than 1, then you don't have this condition. But still, my experience with stochastic algorithm is that you still have to calibrate this. So why am I mentioning this? Is that because what was interesting is that you can easily compute the Hessian of your criterion at this star, and you end up with a formula which is like this. And what is nice is that if you are a statistician, if P is a vector of probability, then, what you can see here is that you have something which is not far from what I call the covariance matrix of a multinomial distribution. So when you have a multinomial distribution, underlying this multinomial distribution is a probability measure P. And if you look at the covariance matrix of your multinomial distribution, then it is something like this. Okay? So it's a matrix which is P times P transpose minus the diagonal matrix made of the elements of P. And actually, it was quite interesting to see, sorry, I've not mentioned the reference here, but you have people who have studied the eigenvalues of this kind of matrices. Okay? And if you look at the existing result in the literature, you can have a nice control of the smallest eigenvalue. It's controlled like this, so it depends on epsilon, and it depends on the minimum value of the target distribution nu. Okay? So in this sense, it gives a way to choose the value of gamma. Okay? This is the choice that we have taken. Okay, so now I think that our main contribution is probably this one. We have proposed, because our goal was, rather than estimating the vector v, our goal was rather to estimate this functional, and we have proposed a simple recursive estimator, which is given by this formula. So it's very simple to update the estimator when you have new data coming. And actually, you can prove almost sure convergence of these things. And you can also prove a central limit theorem with an asymptotic variance, which can also be estimated. And I will show you a simulation explaining why this can be useful to also have an estimation of the asymptotic covariance. Okay, so this was the first results, the first interesting result, I would say, in our work. And the second one is when you look at the literature on stochastic optimization, very often people, they try to analyze the quality of an algorithm by looking at what they call the expected excess risk, which is defined here by this quantity. You want to estimate the value of the functional at V star, which is just this regularized Wasserstein distance. And I would like to see how in expectation this estimator behaves. And you can easily prove that it is given by this formula, which is here you recognize the expected risk at each iteration of the vector given by the sequence of the Robbins-Monro algorithm. And what is happening here, it was mentioned, of course, in the paper by Jérémie and his co-author. What makes the problem a bit difficult is that the objective function, it is not strongly concave or convex, it depends how you see the problem. But what I think it was mentioned in the book by Gabriel and Marco. I read this sentence, and it was written that actually it is not strongly concave, but it satisfies a generalized self-concordance property that has been analyzed by Francis Bach to propose an alternative of the assumption of being strongly convex. So what does it mean? When you have a standard stochastic optimization problem, when you don't have strong convexity, then you can prove that you have a convergence rate of the risk of the order 1 over the square root of n. When you have strong convexity, then this rate, it moves to 1 over n. But when you are in between, when you have no strong convexity, but something a little bit stronger, can you improve this rate? And actually, it is possible if you can prove, for example, it is taken from, the terminology is taken from this paper, if you can prove that your objective function, it satisfies something that is known as a self-concordance property, which has been proposed originally by Nesterov. So I know there are people doing optimization in this room, so I just wanted to add a slide explaining what I mean by a generalized self-concordance. So what did we use? What did we prove for this objective function? Actually, we proved two things. We proved that you can, in some sense, linearize the gradient around the V star, and you have a control of this linearization, which depends here on epsilon square, and of course on the distance between V and V star. And here, what is interesting, here you see why you are losing strong convexity. If you are, concavity, but let's say strong convexity. If you were strongly concave, okay, then you would have this inequality holding for without any condition, and here you will have the constant rho star, okay. But here you see that you don't have strong convexity, and you see two different behaviors, depending on the distance, in some sense, from V to V star. So I don't know if I can explain it this way, but let's say if V is close to V star, let's say A is small, here smaller than 1, then actually this term here, because of this lower bound, when epsilon goes to eta goes to 0, it becomes close to rho star. But on the other hand, when A gets bigger, when you move away from this star, then your convexity constant, it goes to 0. Okay, so there is some balance here. Okay, and we have used this property to prove that under some assumption on the learning rate, you can have a better rate of conversion than 1 over square root of n. Okay, so this is what you have done. So now, if we go back to examples, okay. So just to illustrate the thing, but you are taking samples from an absolutely continuous measure, and you have here an example of the behavior of the algorithm using various values of the parameters epsilon, and here I took the L2 cost. Okay, so what does it mean here? The horizontal lines, they represent the objective value. Well, I'm not completely honest when I'm saying that, because I had to compute this thing which represents the true regularized Wasserstein distance between an absolutely continuous measure and a discrete one. And actually, it's a difficult problem. I don't know exactly how to solve it, except using, for example, stochastic optimal transport. So what I did here, I've just discretized this measure, and then I used the Sinkhorn algorithm to compute the regularized distance between the discretization of this measure and u. Okay? And here you have the evolution of the algorithm, and here you see the interest of estimating the variance, because in this way you can give confidence intervals. Okay? So you can see that when you increase the number of iterations, you reduce the variance of your estimate. Okay? Okay, so now when you have done this, then you can come back maybe to the question at the beginning of this talk, which is the estimation of an optimal map. So here I took the quadratic cost, and this is an estimation of the optimal map after this number of iterations. And what I call here an estimation of the optimal map, it is obtained using the Laguerre Cells formulation of the computation of an optimal map. So recall that our objective was to estimate the true map, which amounts to estimate the true Laguerre cells, where here you have a minimizer of the true Wasserstein distance, which is the maximization problem, but without here the regularization parameter. So what you can do simply is very naive. You think that this is like some sort of estimation of this thing, but you have to be careful, because here all what I'm doing is with epsilon being fixed, okay? And this is known to converge to a maximizer of the regularized problem, and what I want to estimate, in some sense, is a maximizer of the unregularized problem. So this is a question that I have: how is it of interest, and can we study this kind of stochastic optimization problem when we let this parameter go into 0? Okay, so now I will now show you some example of results on the real data, and I will come back to this problem of choosing this epsilon. Okay, so back to this problem. So here, for different values of epsilon and for the L2 cost, so you have an example of the convergence of the algorithm, and again here the horizontal lines are not really the true target. They are just the Sinkhorn distance, or the Sinkhorn distance between this discrete measure over the red triangles and the discrete measure over the blue points. Okay, so you have something like this, and then okay, I can show you the evolution of the Laguerre cells over the iterations for this value of epsilon and for this cost function. Okay, so you can do this for another cost function. You can move from the L2 to the L1 cost function, and you see that you have boundaries which are which depends on the shape, I would say, of the L2 or L1 ball on R2. Okay, so you can, depending on the choice function, on the choice of the cost function, you have different Laguerre cells and different boundaries. But more interestingly now, here on the left I have the L2 cost, the Client cost. Here I have the L1 cost. And what is happening now if I change the value of epsilon? So when you change the value of epsilon, then obviously you change the boundaries. Okay? So here again you change the boundaries, and then here again you change the boundaries. Okay? So then the other question I have is it of interest? I don't know if it's of interest, but how do you choose the regularization parameter in this case? Okay. And for this, yes, I still have a few minutes. Yeah, it's okay. Yeah. And for this, I would like to mention another work that we have done recently on a simpler problem about choosing in a data-driven way, the regularization parameter in optimal transport problem. So now I will come back to another problem, which has been popularized by Guillaume Carlier, Martial Ageg, and then by Gabriel and his co-author, which is the problem of using Wasserstein barycenters for data analysis. Okay? Okay, so what is the problem of Wasserstein barycenters? So imagine that you have a set of discrete measures with support on some space. So you have a sequence of n measures. N measure is a discrete measure with pi support points. Okay? And what you can do entropically regularized Wasserstein. You can use, this notion of regularized Wasserstein cost to define what I would call a regularized barycenter. So let me denote this by a Sinkhorn barycenter. So what is the meaning of a Sinkhorn barycenter? It says that, okay, I'm choosing my Sinkhorn function with some fixed value of epsilon, and I'm looking for a probability measure which is going to be the one which achieves the smallest squared distance, regularized distance, to the data point. Okay, so it's just a generalization of the usual notion of a mean of a barycenter. It's called a Fréchet mean in a metric space. And here I repeat again the formulation, the Kontogorovich formulation of the regularized optimal transport problem. Okay, so now the question is how to interpret epsilon as a smoothing parameter. Okay? So if you had a course in statistics, it is very clear that someday you have seen this problem. You have a sequence of IID variables sampled from a density f. Okay, and how do you estimate f? You do kernel density estimation. So you compute an estimator which is of this form. So you compute this. And then an important question is how do you choose h, which is called the bandwidth parameter. Okay? And I mean, maybe it's the only thing that statisticians do. What they do, statisticians, they say, okay, I have a bias, I have a variance, and h should be the good compromise between bias and variance. Okay? And because I am a statistician, the only way I know to choose a parameter is to do this. Okay? So the question now is how you can estimate, in some sense, the bias of this estimator, and how you can estimate, in another sense, the variance of this estimator. And this is something that we have recently proposed in this paper. So just to give you an idea, imagine that I have a sequence, I have 15 random discrete measures. So what I did is the following. I've taken one-dimensional Gaussian mixtures, which are random because I randomly choose the means and the variances. Okay? Then once I have created this random mixture of Gaussian, I sample points from this Gaussian mixture. And what I represent here are histograms with a very large number of bins. So here you can see the two modes of each mixture of Gaussian. Okay? And now I would like to compute some sort of barycenter of this data. And because I only have a Gaussian mixture with two modes, I hope to obtain an average, which is also a Gaussian mixture with two modes. Okay? But to do this, I have to do some sort of regularization. So here, I show you for different values of the regularization of epsilon, the shape of the Sinkhorn barycenter. And if you have already done a kernel density estimation, then clearly you see here that you have some sort of under smoothing, and here you have over smoothing, and you have to choose something in between. And actually, there is something that I found really interesting. It's called the let's say the Lepski principle. Okay, so and the Lepski principle is something very general, which is like the L curve criterion in inverse problem, and actually it works very well for inverse problem also, the Lepski principle. And to apply this principle to select a regularization parameter, you really need to have an estimate of the bias, an estimate of the variance, something which balances well between the two estimates, and then you can minimize this thing, and this is what we have done here. And then you say, okay, the right choice of epsilon should be this one, and you have this. Okay. And if you want to learn more on the Goldenshluger-Lepski principle, for density estimation, I can mention this very good recent reference. And actually here, how do you, just to be very quick, how do you estimate bias and variance? Well, the variance term is just an upper bound on the variance of this, which is doable. You can have this. And to estimate the bias, you have this idea, which is as follows. When you want to estimate the bias at epsilon, you take regularization parameters which are smaller. You do pairwise comparison, and you subtract the variance at epsilon still. And this is, you can prove that in some sense, this gives you a good estimation of the bias. Okay, so to be honest, here you have to choose another tuning constant. And here, either you take the point of view of mathematical statistics and you say, okay, to choose B, I will obtain an oracle inequality, and this is something that we have done. But I don't know. I don't know what to think of oracle inequalities to choose in practice tuning parameters. But I mean, you can justify the choice of B using this concept, and this is done in this paper, and this is something that we are currently doing in this paper. Okay. But just to okay, so yes, maybe it is not really of interest because these are the real data that we have analyzed. But I will not have the time to present them in this paper. So so it works for real data analysis. And I just want to conclude the talk with this slide. For example, for the L1 cost, which value of epsilon should I choose? What is the notion of bias, the notion of variance, where I want to estimate an optimal map? I have no idea. Okay, so thank you.
Questions? Gabriel?
Okay, so it's a small question, but I was wondering, in your last definition for the Wasserstein barycenter, you used the relative entropy with respect to the marginal, but then it means you use the relative entropy with respect to the barycenter, which is possible, but it's very complicated, so do you really use it?
No, sorry, it's a mistake. Thanks for in the paper, actually, we use the here we use, sorry, yeah, here we use the entropy here. We use the entropy. So that was your question?
Yes,
yeah,
it's a very good mistake.
Yes, you're right. Here we use the entropy. Yes, we use the entropy here.
Because I think it's a very good idea to use it, but so it's still convex, but Sinkhorn cannot be applied anymore, so...
Yeah, you mean if we really use this?
Yes, if you use the barycenter itself to regularize itself. So it's still convex, but Sinkhorn doesn't work, so...
Okay, say it again. Here you say I should really use this.
Well, I'm just saying that I don't know of an algorithm that can solve it.
Okay.
But at very least, it's still a convex problem, and you could probably use your theory, and because Kullback is convex with respect to the product. So.
Okay. So first, to be honest, because I've not been precise enough. Actually, what we are solving is not this problem. We're always working on discrete set. Huh? Okay, first of all. And actually, we have not done this. We are thinking of using this because when you look at the dual potential of the Sinkhorn divergence, when there is only the entropy term here, they're not bounded, I think. And it has raised some difficulty in the analysis of this criterion. Actually, what was happening here is that, okay, we really use this, and so we use the entropy. And actually, we had to prove that you had some Lipschitz property of this loss here, but we have to restrict to probability measures which are strictly positive on the simplex. And we're thinking of using this to relax this assumption. But actually, we have not done that because I was thinking that if we replace the entropy by this, we will see troubles arriving also. So I don't know.
Okay, thank you.
Question? Okay, so I have a few actually.
Yeah, sorry, I forgot to mention something because it was sorry, because you're asking me a question. So before your question, so I forgot to mention that this is a conference on imaging, and Bruno and his co-authors, they have applied a semi-discrete stochastic optimal transport to texture synthesis.
Yeah, okay. That was not...
Because I wanted to mention this.
So now I have no question anymore. No, it's okay. So yeah, actually, so we did use a semi-discrete transporter without regularization, because then you have an actual map, which can be useful for some applications. And apparently that's what you're looking for also, at least as a visualization of your results. So what can you say if when epsilon equals 0 for the convergence of Robbins-Monro?
Yes. So when epsilon is equal to 0, or when epsilon is going to 0, I don't know what to say. Why? Because things are becoming non-differentiable, and obtaining rates of convergence or asymptotic distribution of stochastic algorithm, I think I look at the literature and I will be happy to discuss with some people who have references on this, but I don't know what to do. Okay. That's really an issue. Because if you look at all these papers doing stochastic optimization, very often they assume that you have at least twice differentiability of the objective function. So I don't know. I don't know what I don't know. Okay. Maybe no. But I mean no. You can do subgradient stochastic descent. I agree. But the question of obtaining faster rate of convergence than 1 over the square root of n, obtaining asymptotic distribution, this is much more involved. For example, yes, obtaining the asymptotic distribution of this thing, when the objective function is non-differentiable, it becomes more involved. And also, and it's very important, when epsilon is equal to 0, you now have unicity of the optimizer. And then things are coming much more difficult, because asymptotically, it's becoming more difficult.
Yeah. Okay.
We wanted to do easy things. That's one explanation.
Okay, thank you. Okay, so let's thank all the speakers of today.